This is a tutorial video to demonstrate the use of the READEX tool suite. To apply the tool suite on a benchmark program, the first step is to generate a filter file that contains a list of regions in the application. The filter file is used to reduce measurement overhead. Following this, the second step is to analyze the tuning potential of the application to detect the presence of interface and intra-phase dynamism. If the application exhibits any dynamism, then design time analysis is performed, which results in the creation of a tuning model. Using this tuning model, runtime tuning is performed during the production run of the application. To generate the filter file, the first step is to prepare the application by building it with Scorpy. Following this, the executing application generates a profile.cubex file that contains information on the application regions. This profile.cubex file is then analyzed using the Scorpy autofilter tool to generate the filter file. Scorpy autofilter is a newly created tool in the READEX tool suite, and it takes 3 arguments as input. First, a threshold value in seconds for the granularity of the application regions specified using the -t switch. Application regions with execution time below this threshold are included in the filter file. The second argument is a name for the filter file to be created, specified using the -f switch. The third argument is the path and name of the profile.cubex file to be used by Scorpy autofilter tool. For example, the steps to generate the filter file will now be demonstrated using the cryptkey proxy application. First, the application is prepared by prefixing the build command with Scorpy. Consequently, Scorpy profiles the application during its execution and generates a profile.cubex file. The profile.cubex file contains information on the execution times of the regions in the application. To generate a filter file using this profile.cubex file, the Scorpy autofilter tool is applied by specifying a threshold value, a name of the filter file to be created, and the path to the profile.cubex file. Here, the threshold is specified to be 10 millisecond, and the name of the filter file that will be created is scorpy.filt. Upon running the Scorpy autofilter tool, the filter file contains a list of region names whose execution times are under the threshold value that was specified. This step may be repeated multiple times by running the application with the filter file that was generated in the previous run until no more fine granular regions are further added to the filter file. To analyze the tuning potential of the application, the first step is to annotate the phase region in the application using Scorpy instrumentation. The phase region is annotated using the Scorpy user OA phase begin and Scorpy user OA phase end directives. Here, phase region name is the label used to identify the phase region. Following this, to build the instrumented application, the options online access and user are used when preparing the application with Scorpy. Before running the application to analyze its tuning potential, the Scorpy environment variables to specify the format of the cubex profile file, the puppy matrix to measure, and the name of the filter file to use are to be set. Presently, the cubex profiling format is set to cube tuple, and the puppy matrix to measure are the total instructions count and the total L3 level cache misses. The name of the filter file to be used is the same as the one generated using the Scorpy autofilter tool. Following this, run the application and this generates a profile.cubex file. The profile.cubex file is analyzed using the READEX time detect tool to detect interface and intraphase dynamism in the application. READEX time detect is a newly created tool in the READEX tool suite and takes multiple arguments as input. The -t switch is used to specify a threshold value in seconds for the granularity of the application regions. Regions with execution time higher than this threshold are considered as significant regions for dynamism detection. The -p switch is used to specify the phase region name, which is the same label used in the annotation step to identify the phase region. The -c switch is used to specify the threshold for variation in compute intensity to characterize it as dynamism. The -v switch is used to specify the threshold for variation in execution time. The -w switch is used to specify the required weight that a region's execution time should have with respect to the execution time of the phase in which it appears for dynamism analysis. The result of READEX DynDetect can also be summarized as a report using the "-f switch by specifying a LaTeX file name for the report. And finally, the path and name of the profile.cubex file to be used by READEX DynDetect should also be specified. When the READEX DynDetect tool finishes, in addition to printing its result on the standard output, it generates an XML file titled readex_config.xml, and this is used by the PTF tool in the next step for design time analysis. In the CryptKey application, the body of the main for loop in the sweep solver function can be annotated as the phase region using the scorp user OA phase begin and scorp user OA phase end directives. Following this, the instrumented application is prepared with scorp by using the online access and user options. Now, after setting these environment variables, executing the application generates a profile.cubex file for analysis by the READEX DynDetect tool. Following this, we apply the READEX DynDetect tool with the arguments shown here. The name of the phase region is loop as specified in the phase region annotation. The granularity threshold for significant regions is 500 millisecond. The threshold for compute intensity variation is 10%. The threshold for execution time variation is 10%. A region's execution time is required to be at least 10% of that of the phase. And finally, the location of the profile.cubex file to analyze. The result of READEX DynDetect on the standard output includes information about the significant regions and phase regions in the application. For instance, the report here includes the minimum and maximum execution times of all significant regions that are identified, along with the standard deviation, compute intensity, and weight of their execution times as a percentage of the phase execution time. Similarly, the minimum, maximum, mean, and standard deviation of the phase execution times are also listed. Finally, the summary states if interface dynamism has been detected due to variation in execution times of phases, and if intraphase dynamism has been detected due to variations in execution times or compute intensities of the significant regions. As mentioned earlier, the READEX DynDetect tool also generates a configuration file called readex_config.xml. Under the main configuration tag, the READEX DynDetect tag summarizes the results of applying READEX DynDetect tool on an application. This includes the intraphase tag that contains information about each significant region that was analyzed, the interface tag that contains information about each phase during the application's execution, the threshold values that were used for dynamism detection, and the regions that exhibit dynamism due to variation in execution time and compute intensity. In addition to the output from the READEX DynDetect tool, the READEX configuration file is also used to specify inputs to the design time analysis phase as explained in the following section. To perform design time analysis using PTF, the first step is to include in the READEX configuration file parameters for the tuning plugin that is used by PTF. The AlphaPrototype comes with 3 predefined tuning parameters for the CPU core frequency, uncore frequency, and the number of OpenMP threads to be used for the application's analysis. The users of the tool suite can extend this by implementing their own plugins to include other tuning parameters and specify them in the READEX configuration file for their use by PTF. Optionally, the user may also specify a list of objective values to be measured during the PTF experiments. For example, energy consumed, execution time, product of energy and delay, product of energy and delay square, and CPU energy. If unspecified, then energy consumption is used as the default objective. Following this, scorp environment variables to specify the energy measurement infrastructure, the substrate plugin, and a list of tuning plugins to be used are set. With these in place, PTF can now be applied on the application's executable with the following arguments. The app run is used to specify the application's executable. The MPI numprocs is used to specify the number of MPI processes. The OMP num threads is used to specify the number of OpenMP threads to be used. The phase argument is used to specify the name of the phase region in the application. The tune argument is used to specify the tuning library for PTF to use. And the config file specifies the READEX configuration file name that was created for use by PTF. In the READEX configuration file, the predefined tuning parameters can be set as shown here. For example, the core and uncore frequencies are specified here using the minimum and maximum frequencies along with the step sizes. Also specified in the updated READEX configuration file are objective values to be measured during the PTF experiments. Having set the environment variables to specify the energy measurement infrastructure and the substrate and tuning plugins, PTF can now be applied on the application executable. The standard output from PTF gives the static best configuration for the application. It also includes a summary of the experiments performed by applying different configurations of the tuning parameters for the phase and the resulting objectives measured for each experiment. Also, the best configurations for the individual runtime situations of the significant regions are identified and listed with their measured objective values. Here, a runtime situation RTS is an execution instance of a significant region. Following this, PTF presents the static savings for the runtime situations by using the static best configuration compared against the default configuration, the dynamic savings for the runtime situations by using their individually best configurations compared against the static best configuration, and the overall static savings for the phase by using the static best configuration compared against the default configuration. These savings measured from the design time analysis experiments may be used as an estimate of the potential savings that can be achieved by tuning the application's execution. The design time analysis using PTF also results in the generation of a tuning model file called tuning_model.json. The tuning model generated by the AlphaPrototype consists of three parts: a list of significant regions in the application that are to be tuned, a list of runtime situations, each of which is classified into a scenario, and a list of scenarios, each of which is associated with a configuration that specifies a value for each tuning parameter that is to be set for an RTS belonging to the scenario at runtime. To perform the runtime tuning of the application during its production run, the first step is to set the Scorpy substrate plugins as the READEX runtime library. Following this, the list of plugins to be used for the runtime tuning are specified. Finally, the path and name of the tuning model file are specified before running the application. The application can be tuned during its production run by setting the READEX runtime library as the Scorpy substrate plugin along with the plugins to be used for tuning. Also to be specified is the name of the tuning model file that was created from the design time analysis. Following the production run of the Kripke application using the READEX runtime library, this is a quick illustration of the results visualized using Vampire. The graphs on the left visualize the Kripke application's run without any tuning, while the graphs on the right are that of the run tuned by the READEX runtime library. Here, we observe that the power consumption on the blade for the untuned run is between 260 and 290 watt, while the power consumption on the blade for the run tuned by the READEX runtime library is lower between 150 and 250 watt. Also illustrated are the runtime switchings performed for the CPU core frequency. On the left, we observe that for the untuned run, the CPU core frequency remains at the default value of 2.5 GHz for the Haswell processors, while on the right, the READEX runtime library tunes the CPU core frequency between 1.2 and 2.4 GHz as specified in the tuning model for different runtime situations. Similarly, the uncore frequency remains at the default 3 GHz for the untuned run shown on the left, while it is tuned between 1.2 and 2.4 GHz by the READEX runtime library as shown on the right. In this evaluation, by comparing the energy consumption of the Kripke application tuned using the READEX tool suite against an untuned run of the application, the total energy savings are observed to be around 10%. Further information on the READEX project and the tool suite can be obtained from the website www.readex.eu.